solve the first question in electric potential chapter. It is a charge distribution over 1/3 of a ring. And let me draw the figure. So it's going to be something like this, where it's located at a distance of r away from it. And it's 1/3, so it's 60 degrees here and 60 degrees. So total, it's 120 degrees. And it's all positively charged, where the charge distribution is basically given by a uniform charge distribution that is lambda. And we are asked to find out the potential at point P. So what is Vp? In terms of obviously lambda, and possibly r and epsilon 0, so the constants, okay? Before proceeding, let me remind you what the definition of the electric potential was. For a single charge located at a distance of r, it is equal to either k, q divided by r, or in terms of k, we write 1/4 pi epsilon 0, right? Q divided by r. And I have to say, electric potential, or any potential in and itself, is not a meaningful quantity. It's always between 2 points, right? It's potential difference between 2 points. But for realistic situations, let me write it, for realistic situations in quotations, what we calculate in almost all cases, except unrealistic ones, which I'm going to talk in a moment, we talk about the potential difference between r and infinity. Since the effect of electric charges at infinity is 0, it is safe to talk about the potential at a point r, and that's what we are doing. And I told you that I'm going to talk about the unrealistic situation is, and that's basically the following. If you have like an infinitely long cable, like a charge distribution which we assume to be infinitely long, which is unrealistic, right? You never have an infinitely long cable. But what we mean by that is they're close enough to that cable so that wherever we look, we see that cable, and that's why we kind of assume that it's like infinite, but that's not really true, right? Okay, so for these, except these unrealistic cases, it's always safe to assume the electric potential at a distance r away from the charge is given by kq/r, okay? So let's do this. The idea is, again, exactly the same idea that we used last time. We take the effect of an infinitesimal part of this object and then integrate for the whole thing. Okay, so I'm going to start with taking a random point, which is this guy, and it will have a charge of dq, okay? And it's located at a distance also r away from P, right? As you can notice, all of these points are located at the same distance r away from that. And we will see in a moment that it will give us a chance to evaluate the integral without doing any work. So, okay, so let's start with the effect of dq here. dV, which is infinitesimal potential, is equal to k times dq divided by the distance dr. And we are asked to calculate Vp, which is all these guys added up. So I have to integrate that, both of these sides, to get V, right? So now I have to take the constants out of the integral, right? And you can see that k is a constant, obviously. And that is k divided by r, and only dq stays inside the integral. I also took r out of the integral because they're all located, all these dq's, which are randomly chosen, are always same and located at the same distance, r, away from P, right? And this integral gives us the total charge, Q multiplied by K divided by R. So that's Vp. Okay, so we're almost done. So let me write the final form in here. V at distance P is equal to K times the total charge on here divided by R. This looks like a single charge, and it makes sense, right? It's exactly the same thing as if all of this charge is located at a distance of r away from P, because the shape here is kind of, irrelevant, right? Because all of them are located at equidistant, And that's why we get exactly the same formula with a single charge. The only thing that now we are missing is how to relate this lambda to this q, and that's simple. As you remember, in 1D, line charge density, which is lambda, multiplied by the length of that, whatever one-dimensional charge distribution is, gives us q, right? So that's why here, instead of q, I'm going to substitute here. And what is the length in here? Length is the total length in here, and it's 1/3 of a circle. 1/3 of the circumference, right? Oh, let me write down this. Circumference of the circle. So if it had been a circle, it would be 2 pi r, but it's not a circle, it's 1/3. And that's why we get lambda times 2 pi r divided by 3. So at the end, Vp would look like the following. And instead of k, I'm going to put down 1/4 pi epsilon 0. And I'm going to multiply that by lambda, 2 pi r divided by 3. And I'm going to divide everything by r, right? R here is in the denominator. Let me make some cancellations right here. So you see this 2 pi gets canceled by 4 pi here, and I get 2 here. And r gets canceled with the other r here. And all I'm left with is the following. V at point P is equal to lambda on top. 2 times 3 is 6, and I only have epsilon 0 here. Okay, so we get a very simple expression at the end.